Okay, this video runs through the worked solutions for the practice assessment for Applications Assessment Standard 1.4. Question 1 here gives us a function which is used to calculate the volume of a cylinder. Now, don't worry about the appearance of pi here. Of course, pi is just a number, and it shouldn't put you off as we go through this process. Now, we're asked to find the value of x which maximises the volume of the cylinder, so the key word here is certainly maximises. That is your clue to tell you that this is an optimization type of question which is going to require differentiation. Now you can probably see this hashtag 2.1 here. That's a mark for you demonstrating that you know how to approach this type of question. There's then also 3 further processing marks. So first step here would be to check that the function is ready to be differentiated, which it is. Both terms here are written in the form ax to the n. Notice that it's a function called v of x, so when we differentiate we're going to end up with v dash of x, and differentiate as normal, so multiply by the index and then subtract 1, gives us 18 pi x across the first term, minus 3 pi x squared on the second term. Now we have the derivative. This is a formula which represents a gradient. We're looking for stationary values because we're hoping one of those stationary points or stationary values is going to be where a maximum occurs. So the stationary values or stationary points, they occur when the gradient is equal to 0. The gradient is of course v dash of x. So it's good practice just to note down there that you know when the stationary points occur, and that's communicating to anyone who's marking your work that you understand what's going on. Then set your derivative equal to 0. So we're going to take 18 pi x, take 3 pi x squared, set that equal to 0. And as is so often the case when solving equations like this, factorising is going to help. There's a common factor here, highest common factor of 3 pi x. So we can divide that out across both those terms, leaving us with 6 minus x. We've got these 2 factors, and then taking each factor separately, set them equal to 0 and solve them for x. This one gives us x equals nothing, 0 divided by 3 pi is nothing, and the 6 minus x factor will solve here, subtract 6 from both sides, divide both sides by -1, gives us x equals 6. So we've got stationary points when x is 0 and x is 6, and hopefully one of these is going to give us a maximum. But to find that out we need to create a nature table. Now constructing the nature table is very important, that you put in all the relevant information. So in this case it was a function of x, which is fine, we can use x up here, and no dy by dx here. Y doesn't mean anything in the context of this question. We need v dash of x, and then we're going to work out the shape and then ultimately the nature of this thing. So we know we've got stationary points at 0 and 6, and we can plug them in there, but what we're really interested in is what is the function up to as it approaches 0, as it goes from 0 into 6, and then what happens beyond 6. We can examine the gradient on either side of these stationary points and decide whether these stationary points are maxima or minima. Now the way to do this is to choose a value, a sensible value that's just a little bit below 0, so I think -1 is probably a good option there. Something between 0 and 6, so we'll take 1, and something just a bit beyond 6, so 7 I think is a good value. And what you can do here is substitute these into your derivative, the gradient here. And what I like to do certainly is use the factorised version because, well, as you'll see, it's quite easy to find out whether the derivative is positive or negative. So in the first case, -1, substituting in here for x, well, we can see that that first part of the derivative, that first factor, will be negative, and 6 take -1. Well, that's 7, that's a positive value, so we're going to have negative here multiplied by positive gives us a negative value. Now we know that we've got stationary points at 0, and just to double check that, if we substitute 0 in here for x, this first factor will go to 0 and 0 multiplied by whatever that second factor is will still be 0. Taking our 1, 3 pi times 1, well, that's a positive value. 6 take 1, that's 5, that's also positive. So two positives here, two positive factors multiplied to give us a positive result. 6, well, we know that's going to give us 0, but you can see there, if you substitute 6 into that second bracket, that'll take it to 0, multiply by the first factor. Definitely 0 in there. 7, well, 3 pi times 7 is positive, and 6 takes 7, that goes negative, so we've got positive multiplied by negative here, giving us a negative value. That means that we've got negative gradient, a flat section there at the stationary point, and increasing stationary and then down again. So we can see from the nature table that we've got a maximum here when x is equal to 6. This question only asked us for the value of x, so we're finished in this case. Although you may also, in another question, be asked to find that maximum volume, and that would need you to take x equals 6 and then substitute that back in to the original equation, the one here that worked out for him. So you would be finding v of 6. Substituting 6 in for x here and here would give us the maximum volume of that cylinder. Moving on to question 2, quite a complicated function actually here, producing this curve, part of the curve shown here, and we're asked to find this shaded area. Integration is the way to do this, to find the area between a curve and the x-axis. We're lucky because we know the limits here. This is 0, we can see the curve crosses the x-axis at 0 and at 2, so we've got our limits of 0 and 2, and we just need to set up the integral. Now, in this case, the function's been given to us in a factorised form, which is actually very useful if you want to find the limits, but we can read them from the graph. So we're going to have to multiply this thing out first of all before we can think about integrating it. You don't want to tackle integrating something like that. Multiplying it out should make it much more accessible. So I just rewrite the integral first of all here. We're integrating between 0 and 2, and x cubed, x take 2 squared. All of that should live in a bracket, and don't forget the differential there, dx. If you miss off dx, you will be penalised, so it is a very important part of the integral. Now we'll start multiplying this thing out. Hold the x cubed at the front just now and square out this bracket. Now you might want to write out the bracket twice and do the 4 multiplications to tidy it up, or you might have the shorter method here where you can square the first term, giving me an x squared, then multiply these two terms together, which makes negative 2x, and double that, negative 4x, and then finally squaring that last term gives us a positive 4. That's the quick way of squaring out a bracket like that. Square the first term, and then we say twice the product of the terms, that's where the 4x came from, the minus 4x, and then square the last term. All of this should still be in a bracket, and that differential is still there, dx remains. We're almost there. We're just going to multiply the x cubed through this bracket here, so using the distributive law, multiplying x cubed in here gives us x to the 5, it's a little bit of index work for you here, just 3 plus 2 giving that index of 5, then minus 4x to the 4th power, and plus 4x cubed still lives in the bracket, dx still there, and now we can't simplify this any further, so we're ready to integrate it in the normal way, which means we don't need the integral sign anymore. Integrating x to the 5 will give us x to the 6 over 6. 4x to the 4 will go to 4x to the 5 over 5, and integrating this last term, 4x cubed, will go to 4x to the 4 all over 4, which is quite nice because I think we can see that there's going to be some cancelling there. They'll disappear and that'll leave you with x to the 4. And must remember that we've got our limits of 0 and 2, so we're now in a position to substitute in these limits, starting with the upper limits. We've got 2 to the 6 over 6, 4 lots of 2 to the 5 over 5, and then adding on the 4's have cancelled there, so we've got 2 to the 4 in a bracket. Now you might spot already that substituting 0 in for x to these three terms will ultimately give a 0, but you must acknowledge that by showing that you've remembered that lower limit, you've substituted in, and you've gone to 0. Now, you've got the calculator for this, but I would certainly recommend working out these, at least the numerators, just so that there's no mistakes when you're keying into your calculator. You should know the first few powers of 2, and 2 to the 6 is 64. That's 6 2's all multiplying by each other, gives you 64 over 6. In this case, 2 to the 5 is 32. 4 lots of that, 128. That's over 5. And then 2 to the 4 is 16. So you can work away on the fractions there if you want, getting the common denominator, or use your calculator to work out 64 over 6, take 128 over 5 plus 16, giving us a final value here of 16/15. That's simplified, that's fine. So it's quite nice here. We were asked to find a shaded area. Area equals 16/15, or 1 1/15 if you want 16/15. But what's very important here is that we remember we've got square units. Area measured in square units. So moving on to question 3. You have two curves here, and we're trying to find the area enclosed by those two curves. Again, we've been told that the curves meet at x equals 1 and x equals 3, so they're going to become our limits. And I think it's important for us just to take a moment to make sure we know which curve is which. This red curve, this N-shaped curve here, is a parabola. An N-shaped parabola should have a negative x squared term, so the red curve is going to be this one, 9 take x squared, which means that the U-shaped parabola that we've got coming through here will be given by this equation here. Now, when you're trying to find the area enclosed by two curves, we will be integrating, and it's good just to try and think of it as the integral of the upper curve minus the lower curve. So what I mean by that is between the limits that we're interested in, we examine this area and see which curve forms the upper bound. So in this case it's the red one, that's the upper part, and the blue curve will be the lower bound there. So we're looking to try and integrate, let's see if we can squeeze this in here. We're looking to integrate between the limits of 1 and 3 the difference between this upper curve, so that was 9 take x squared, minus the whole of this, the lower curve in this case was the 2x squared. So because we're subtracting everything that makes up that curve, definitely need to put it into a set of brackets, minus 12x plus 18, and to be totally correct, the whole thing should live in another set of brackets, and again dx there is part of the integration, it needs to be shown. Always try and simplify as far as you can before you go on any further. So integral between 3 and 1 of 9 take x squared take 2x squared, and you can see if we'd missed out the brackets here, you might end up with a negative 12x, but actually that should be a plus 12x because of the negative here in front of the bracket, and we end up with a minus 18. All still in a bracket, don't forget the dx. Slowly but surely we're getting there. Let's join these things up with an equal sign. I think one more step before we've simplified it. Having a look at the x squared terms, look at minus x squared minus 2x squared, so minus 3x squared. We've got positive 12x, and then the terms independent of x, the constant terms here, 9 minus 18 gives us minus 9, all in a bracket. Don't forget the dx, we're nearly there. Now, a couple of options here. You could, if you want to, divide this thing by negative 3. That would be okay. You can actually bring a factor of -3 outside of this integral sign, but you might not be familiar with that. And since we've got a calculator, we can just carry on processing through this and start our integration. So the first term, add 1 to the index, takes us up to 3x cubed, and divide by that new index, and you maybe see these 3's are going to cancel quite nicely. Adding 1 to the index here takes us up to x squared, divide by that new index again, there's going to be some cancelling, and then finally, I don't know why I made that plus, we're going to be subtracting 9x, remember constant terms like that integrate to 9x, and the limits are 1 and 3. So I certainly wouldn't go substituting anything in until I'd simplified down a bit. I know these 3's are going to cancel, and this 12 and 2 will also simplify a little bit, leaving us with a 6. So let's carry on. I'll take a different colour. -x cubed plus, now we've got 6x squared, take 9x, and those limits of 1 and 3. We've simplified that as far as we can go, so we can substitute in now. Notice this isn't -x all cubed, this is the negative of x cubed, which is subtly different. So we're looking at whatever the result of 3 cubed is, it needs to become negative. Adding on to that 6 lots of 3 squared minus 9 lots of 3. And then in this case, unfortunately the lower limit wasn't 0, usually quite nice when it's 0, but in this case the lower limit was 1, so we have to substitute 1 in here. Negative of whatever 1 cubed is, plus 6 lots of 1 squared, take 9 lots of 1, and then we can start to evaluate some of this stuff. Again, you could key it all into your calculator if you wanted to. 3 cubed is 27, so we've got -27, 3 squared is 9, and 9 sixes are 54, I think 54 in here, and minus 9 times 3 is minus 27. So I don't know if you've noticed here, but I think this first bracket is going to go to 0. And from that we're going to be subtracting, well, 1 cubed is 1, so minus 1 plus 6, take 9. And we've got enough room just to finish this. We're going to have 0 minus whatever that second bracket turns out to be. That's -1 plus 6, take, that looks like -4. So 0 take -4 is in fact 4, which is good, a nice positive value which we were hoping for. And to finish this question off, the area that we were looking for is equal to 4 square units.